Welcome, ladies and gentlemen, to our lecture on position, displacement, speed, and velocity. So when we think of position, we're thinking of where something is. Consider a point on this page. If we want to describe the position of this dot, we would describe it using some reference point. For example, we might describe it in relationship to the top left corner or to the bottom left corner of this page. So to describe where something is, we must establish a coordinate system. For example, when we describe this dot in relationship to the bottom left corner of the page, what we're really saying is that this point lies some distance x from the bottom left corner and some distance vertically y from the bottom left corner. And we would give those coordinates or those distances. Maybe this one is 2 centimeters and this one is 2.5 centimeters. In doing that, we've chosen a coordinate system. And you should remember that all coordinate systems are established by people. It isn't something that innately exists in the world. It's something that we use so that we can describe the world. In physics, we generally choose coordinate systems that either make what we're considering easy to conceptualize, or, even more often, we choose coordinate systems that simplify the mathematics of a calculation. And this brings me to perhaps the most important thing for you to remember from this lecture. You get to choose coordinate systems, and you should choose them to be to your benefit. What does this mean? Well, remember that when I choose a coordinate system, I choose a number of dimensions appropriate to the number of dimensions I'm working in. So for this page, I might choose 2 dimensions. I give a direction that's positive for each dimension. I have orthogonal directional axes, so they're perpendicular to each other. So when something moves in one axis, it doesn't move at all in the other. And then remember, the other thing I have to have a coordinate system is I have to choose a place to be 0. In our example before, we chose the bottom left corner of the page to be the origin, to be 0, 0 in our coordinate system. When I go to solve a physics problem, I get to choose the origin as well as which directions are going to be the axes of my coordinate system. We're going to talk about motion in a straight line today, so I'm always going to choose my coordinate system along the path of motion. So imagine I'm going to consider a particle that can move back and forth along this line. Now, this is drawn on a 2-dimensional page, so I can choose any 2-dimensional coordinate system that I would like. I could choose a coordinate system where up is y and right and left are x. So x hat right, y hat up. That's perfectly fine, and that works, but you can see now that as my particle moves back and forth across this line L, I'm always going to be moving in both the x and the y direction, so I'm always going to be calculating things in 2 dimensions. So instead of this coordinate system that I've chosen, I could choose a different coordinate system. I could choose one where x goes in the direction of L, and then y hat, I might not even define now because I know that I'm going to only move in one dimension up and down this line. So maybe in this case now I don't even need y, but I've tipped my xy so that now only x matters. I've chosen it so that it aligns with the motion. And remember that when I'm dealing with motion in 1 or 2 dimensions, I should think about aligning my coordinate system so that it lines up with the expected motion. You'll see how this is advantageous as we start solving problems later on in this class. But always keep this in mind. You get to choose the coordinate system, and in this case I'm going to choose it such that it's really easy for me. So if I know that I'm going to have motion along a straight line, I should choose my coordinate system to describe that straight line in as little effort as possible. So now let's go to a horizontal line, just to make things easy on ourselves. And we'll say that along this horizontal line to the right is x hat. So now we've chosen this coordinate system, and think about a point moving from some position xi, or x initial, to some position x final, or x sub f. Now your book really likes to use x sub 1 and x sub 2, but the 1 and the 2 aren't very descriptive, so it sometimes invites some confusion where you're thinking, which one was 2? What order do they go in? How does that go again? And I like to keep things simple by using more descriptive subscripts, and this is a good practice in general. So I use an F for final and an I for initial, and then it's really easy to remember which is which. Final is at the end and initial is at the beginning. It's right there in the name. So I like to use x sub I and x sub f, and as we go on in the class you'll see that we use something called x naught or v naught, and the sub 0 means at time 0. So we'll have x at time 0 equals x naught. But for now, let's stick with x initial and x final. So imagine we have a point on this line, and this point moves from x initial over here to x final. When the point moves, we have what we call a displacement. And a displacement is a vector describing the motion from initial to final. This vector has a length here that we'll call d for now. And it has a direction, and in this case the direction is in the positive x-hat direction. It moves from left to right. This displacement is noted as delta x. This triangle here is delta. This is the uppercase version of the Greek letter delta. Delta x is equal to x final minus x initial. It's always x final minus x initial. It's never x initial minus x final. So we're using x here because I've established the x-hat direction, but we could have, if we had two dimensions, we could also have delta y, where we have y final minus y initial. And let's give some values to these. Let's say x initial is at 1 meter and x final is at 5 meters. You can see that our delta x will replace d down here now with delta x equals x final minus x initial, which is 5 meters minus 1 meter. And you can see that means that we moved 4 meters. And you can see that it's positive. Positive tells us it went in the positive x-hat direction. Okay? It moved to the right. And we can see that's exactly what we've drawn here. You can imagine, by contrast, if we had the same motion, but now we went from x initial on the right to x final on the left, where this is now 1 meter, and x initial is at 5 meters. Okay, so our origin might be somewhere here, 0. Our direction is still x-hat to the right. Okay, once we pick the coordinate system, We need to respect that coordinate system regardless of what happens. So if this was the same motion, say it moved to the right, and now it moves back to the left. So now for this motion to the left, we start at this spot on the right, the 5 meter spot, and we go back to the point on the left. So for this piece of motion, x initial, the thing that happened first, the place that we started, is at 5 meters. So now we have delta x equals xf minus xi. So the place we ended, 1 meter, minus the place we started, 5 meters, and now we have a minus 4 meters. And this is telling us we still moved 5 meters, right? Our particle with these two motions has now just moved to the right 4 meters and then to the left 4 meters. In both cases we moved 4 meters, but now it's negative because the positive x-hat direction we've defined to be to the right. This negative tells us that we moved in the negative x-hat direction. This is why we always write delta x as x final minus x initial, because then the sign will tell us the direction. So again, we get to pick our coordinate system, but once we've chosen it, as we consider the entirety of the problem, we need to stick to it for it to be useful. So once I chose x hat to be to the right, as we considered this particle going back and forth from left to right and right to left, then I stick with that coordinate system. I continue to write things as final minus initial, and the sign on delta x will tell me the direction of the displacement. So now let's look again at our particle moving along a horizontal line. And let's consider, again, a point x initial and a point x final, and we have a particle moving back and forth. But initial and final are describing time, aren't they? I'm saying that one happened first and one happened last. So we have some time, t initial, that's associated with x initial, and we have some time, t final, that's associated with x final. So if we have a little particle and it moves from here over to here, we know that this distance, delta x, is equal to x final minus x initial. But this also took place over some time period, okay? And that time period, delta t, is t final minus t initial. So now we have a distance that was covered, and we have some time interval that it took to cover that distance. We can calculate the average velocity v average, or VAV, using these quantities. It's delta x divided by delta t, the distance that we covered divided by the time that it took us to cover that distance. And this is equal to x final minus x initial over t final minus t initial. The magnitude of this vector is going to be the speed. So velocity is a vector with speed and direction. And speed is the magnitude of the velocity. So in this case, as our particle moved from left to right, we're going to have some speed with the direction to the right. Notice that as we look at this numerator up here is going to have units of meters, right? This is meters minus meters. And this denominator down here is going to have units of seconds. So we have units of length on top, units of time on the bottom. And this is how we get a velocity or a speed, meters per second. Or if you're in the United States in your car, you might have seen miles per hour, again, a speed or a velocity. And if you're not in the United States, you probably have seen kilometers per hour in your car. Again, a length over a time, which gives us a speed. The next thing to pay attention to is note that delta t will always be positive. Okay, delta t is greater than 0. And this is true because time always flows forward. We don't have time flowing in reverse, right? Time flows forward, so delta t is always greater than 0. What this means is that V average will have the same sign as delta x. So the direction of the average velocity will always match the direction of the displacement. And this makes intuitive sense, right? If the average velocity is describing our motion, and our motion took us from left to right, we expect that our average velocity should point from left to right. So now let's consider plotting our position in this same horizontal motion, left and right, as a function of time. So note that in a plot like this, we're not plotting the path of the particle. The particle is just moving back and forth along this line, okay? What we have is a visualization of how its position is changing in time. So imagine now we're going to set up a coordinate system that's advantageous to us when we consider this. So if our particle is starting in the center and it's moving to some point x final, I'm going to choose the origin x equals 0 to be at x initial because that makes things really easy. So let's put x initial at the origin where x equals 0. And then let's say it moves some distance up here to x final. Okay, so this first point that I've drawn, we have no time passing. We know that this is not physical. We can't move from one place to another without time passing. And we see if we try to calculate the average velocity, delta x over delta t, we'll have x final minus x initial, and that'll be some distance. You can see there's a distance covered here along the y-axis, over t final minus t initial. But you can see here we haven't covered any distance in the x direction. So t final equals t initial, which means we'll have x final minus x initial over 0, or infinity. So our average velocity then is infinite because we've covered distance in no time. So we know that's not going to be the case. Now let's consider moving in just a little bit of time. So we still have the same x final, but now we've covered it in this much time. So now we do have a velocity here. We have some distance, xi to xf, this distance right here. okay, over this distance in time. And you can see if I put this point out here, I've covered the same distance, delta x, but now I've covered it in even more time. And you can see if I put the point even further out here, I've still, again, covered the same distance, delta x, but now I've covered it in even more time. So what's going on here? You can see that as I move this point out to the right, the slope of these lines is changing, right? The slope of a line, remember, is rise over run, or the change in the vertical direction divided by the change in the horizontal direction. So if we look at our plot, the slope is equal to rise over run, which is equal to delta x, this distance that's been covered, divided by delta t, whatever horizontal distance, the amount of time that we took to cover it. But this should look familiar, right? This is average velocity. So if we're calculating average velocity, we're always calculating a line on a plot like this where we have x as a function of t. So now let's look at a curve that we could plot on this. What if our position as a function of time looked like this? That's still a perfectly valid way for this to look, but you can see that the slope on this is always changing. So we have a velocity that's not constant. If we calculate the average velocity, so you can imagine that at some point along the way we're here, and let's call that x final. If we calculate the average velocity, we know that we'll have delta x over delta t. Okay, we know this is delta t. And this is delta x. So we'll have some distance over the time, and we just looked at it and saw that that's the slope of a line from xi through xf. So average velocity is always going to be the slope of a line like this. So in a situation like this where we have this curve and our velocity is actually always changing, if we take the average velocity, we're always going to be taking a line between the 2 points instead of maybe the curve that was actually happening. Now we can make this line get closer and closer to the curve by taking points that are closer and closer together. Right? So as I take points that are closer and closer together, the curve is less and less different from the line. But always remember, when I calculate average velocity in this way, I'm always calculating in a straight line here on a plot of position as a function of time. So that covers our lecture for today. Our concepts of displacement and velocity in one dimension should give us a nice base for discussing some more interesting concepts in the next lecture.